We're really pleased, especially pleased today to have both Jim Anderson and Dan Schrag here from Harvard University. We didn't raid the university, but we wanted to sort of pick their brains about some important issues, I think, that need more vetting, and that is essentially walking around this issue of climate and energy in more detail and looking at it from the lens of energy. In other words, where is the energy going that's going into the system that's creating the heat, and how is that energy distributed, and what are its consequences? In other words, the energy is the focal point of the problem. I mean, down the road, the solutions require how do you restore the energy back from where it came. And I don't want to steal Jim's punchline or Dan's, but we're going to walk through that very carefully, and perhaps at the end of today, maybe rewire some of your thinking about the climate energy issue, and step back from it a little bit and look at it perhaps a little differently. Anyway, without sort of taking up more time, yes, we are videotaping this. This is our first attempt to do a bona fide video, and we hope to offer that video in total on our website in a variety of formats, podcasts. We'll have an audio component to it. We'll have a streaming video, and we'll have the entire thing that you can download and do what you want with. It may not be up there tonight or tomorrow morning, but it'll be up there in some form, presumably fairly quickly. And we'll get better at this as we go on, but we're sort of walking through how to do this, and bear with us for a while, we'll get there. We'll not C-SPAN, but we hope to get a quality product over time. Anyway, having dwelled on that a little bit too much, let me introduce the speakers today. And I'll start with Dr. Anderson, Jim Anderson, who's it's difficult to know where to start because it's just a list of awards for virtually everything and anything in chemistry. He's a member of the National Academy of Sciences. He's the winner of the recipient of the UN award for his achievements in ozone when that program was flying very high, when we had to deal with the ozone hole issue, the ozone depletion issue. Turns out Jim's research pointed a finger and made the case for the role of chlorine and its role in destroying, helping to destroy the ozone layer. So Jim's achievements were recognized worldwide in identifying the problem and getting on with the sort of resolution of it. His specialty, if you would say that, is chemistry, the atmosphere, interactions, and climate change. Our second speaker, Daniel Schrag, is also from Harvard University, as I said. Dan has been working on various aspects of climate change, looking at the big picture. In other words, going back to the history of the planet and looking at climate change through time, what climate change was composed of, how it's evolved over time, what it looked like years ago, and so he's had a really macro-scale look at climate. He's looked at El Niños, tropical Pacific circulation, glacials, interglacials. As I said, he's covered the whole gamut of climate. He's a recipient of a MacArthur Fellowship as well, and put some time in as a faculty member at both Princeton and Yale prior to coming to Harvard University. So without taking up any more time, we're going to try to leave the lights the way they are and start off with Jim Anderson. Jim, thank you so much for coming, both you and Dan.
Well, good afternoon. I should say at the outset that the issue of energy demand and the climate response to that energy demand is both complex and contentious. And of course, almost all of you know that, or you wouldn't be here this afternoon. But at a much more fundamental level, there are similarities, in particular examining the way energy flows through the economic structure and the way energy flows through the climate structure provides a very important scaling and comparison in this endeavor. So what I'd like to do is start out by looking at the unique point in history that all of us share. Of course, modern humans emerged 160,000 years ago, 8,000 generations ago. And the population of the Earth in the Roman period was on the order of 250 million people, and it remained there until the Renaissance. And 1776 is a very interesting year for us, but it's also the year that the world population struck 1 billion. And it reached 2 billion in 1945. And within one human lifetime, between 1945 and the middle of this century, the world population will expand from that 2 billion to nearly 10 billion people. And of course, this is in many ways a number that is very difficult to grapple with intuitively because we haven't seen the impact of this population on the planet. We have very little empirical knowledge or background to judge its importance. And so when we look at this combination in this historical context, this increase in population has to be taken into account with increase in per capita wealth, because it's the product of these two that not only drives the economic engine of the world, it also, it turns out, it drives the impact that the combination of population and the economic endeavor has on the planet itself. So it's very important to stop before discussing this further and recognize what a unique time this is and how important it is to recognize the scale of this problem. So if we multiply this increase in population by average per capita income by the energy demand per dollar of economic output, we can calculate the global economic machine. And the world population now is about 6 billion, and the per capita income is on the order of $5,000. So that's $30 trillion a year economic endeavor globally. So we're immediately into the trillions, and the units that I will use, as you see in the short write-up, are the units of billion, trillion joules, the unit of energy, which is really what the discussion has to come down to. And the product of population per capita income and energy demand is this global energy number in joules. And in 2005, this number was 0.5 billion trillion joules per year of energy. And this begins to set the scale of the problem. And I'll stick to this unit all the way through the discussion because everything scales with it, both in the economic system and in the climate system. So joules are the unit, and we will talk about multipliers of billion, trillion joules. 2050, because of the increase in population to 10 billion and the increase in per capita income to on the order of $8,000 per person, this turns out to be 1.5 billion trillion joules of energy. So what does this mean? The equivalent of this is to determine the rate of increase in the production of energy required to meet this demand. And this demand is actually quite conservative, as Dan will point out to you. Almost every number I present to you is the current acceptable number, and in almost all cases, it's a conservative number. So what does this translate into? Well, to meet the energy requirements in 2050, we have to construct 1,000 large coal-burning power plants per year for the next 40 years. And this is where the scale of the increase in energy demand begins to come to roost. Or we can commission 250 nuclear power plants per year for the next 40 years. So this is on the order of 3 coal-burning power plants per day, or a nuclear power plant every day and a half. And this is the scale that the energy demand thrusts upon us. And this is where developing the intuition for the rate of increase in this energy requirement becomes so important.